Let's now look at non-modularized or end-to-end ASR system. Let's now look at parallelism between task of machine translation and ASR to see how we can build non-modularized ASR system. The goal of machine translation is to translate sentence from source language to target language. In order to do this, we first use an embedding layer to convert each of the source language word in source language sentence to their corresponding embedding. Then we use an encoder to compute encoder state at each of the word in the sentence of the source language. Hence, encoder states encode the source language sentence. We then use a decoder to generate output language sentence, which is the target language, word by word. While generating each of the target language word, decoder has access to history of the words generated so far in the target language sentence and all of the encoder states. In interest of the time, I would not go into details of this, but for more detail, you can check out the lecture from Bhiksaraj at the link in the slide. Now let's look at how we can build a ASR system with such a formalism. Rather than using embeddings from the source language word, we could use audio features at different audio frames as input, and rather than using output as the word in the target language, we could use output as the letters in the language we want to transcribe audio to. And indeed, there is such a system, and this system is called LAS, or Listen, Attend and Spell. One of the observation to be made about LAS is that while generating the output at any decoder step, I am conditionally dependent on what I have seen so far in my output transcript produced so far, as well as all of the encoder states of my audio. So I cannot start to decode or I cannot start to transcribe the audio until I have seen the full observation of the audio. And hence, we cannot build a streaming ASR system in the natural setting of LAS. Let's now look at how we can build a streaming ASR system in a non-modularized manner. So to do this, what we will do is we will build a system which will be able to generate the probability distribution at every audio frame without waiting for the future frames to appear. So let's first look at an example to kind of explain how we can build a streaming ASR system. So let's say you have an audio which has 7 audio frames in it, and then you have passed each of your audio frame or the features corresponding to each of your audio frame through a sequential neural network or some sort of a neural network, and you have gotten an embedding corresponding to each of your audio frame, right? So for frame 1, your audio embedding is F1, for frame 2, your audio embedding is F2, for frame 3, your audio embedding is F3, and so on. And let's also assume that for this particular audio, the true transcript is letter sequence B and E. So now you have an audio which has 7 audio frames in it, and the corresponding transcript to these 7 audio frames is letter sequence B and E. As I said, then what we can do is use a softmax layer to generate the probability distribution over different letters in your language. And for simplicity, let's assume that in English we just have 3 letters. We indeed have 26 letters of capitalized form and 26 letters of lower form and in space. So we have actually a total of 53 letters. But for the sake of simplicity, for this example, we are assuming that let's say we have just 3 letters. So once I have passed the audio embedding through the softmax layer, I would have a probability distribution of size 3. Because I have just 3 letters in my example language, it will assign some probability to, let's say, letter B, letter E, and letter C. So these are the 3 valid letters in my language. And you do it for frame 1, you do it for frame 2, you do it for frame 3, you do it for frame 4, you do it for frame 5, 6, and 7. So what you now have is 7 audio frames, and corresponding to each audio frame you have a probability distribution over your letters in the language. So you have 7 different probability distributions, but you had just 2 letters spoken in the transcript, right? So in other words, the number of audio frames is not going to be same as the number of letters spoken in your transcript, right? So we have just letter B and letter E. So we have 2 letters in the transcript, but we have 7 audio frames. So how do we kind of represent the problem with this kind of dissimilarity between the number of audio frames and number of letters? So in order to still represent the ASR problem, we make an heuristic and we say that we will collapse the continuous occurrences of the same letter into one occurrence, right? So for example, we can say that the letter B was spoken from the frame 1 and frame 2 as well. And since these are the continuous occurrences of letter B, so we will just collapse into one occurrence of letter B, and then we will say that from frame 3 to frame 7 you spoke letter E, and since these are continuous occurrences of letter E, so we will collapse into one occurrence of letter E. In other words, now we are able to represent 7 audio frames into 2 letters in your transcript by using this heuristic. Now, we do not know whether from frame 1 and frame 2 you spoke letter B, or was it from frame 1 to frame 4 you spoke letter B, and then frame 5 to frame 7 you spoke letter E. Since in training what we have is an audio and corresponding transcript, we do not have the alignment, or in other words, we do not know at what audio frame what letter was spoken. So this was just one choice of the alignment which we can make. The other choice is, let's say we say that the letter B was spoken from frame 1 to frame 3 and letter E was spoken from frame 4 to frame 7. So again, these are 2 choices, right? We could enumerate all possible choices which could generate us the valid output sequence of letter B and letter E from 7 frames with the heuristic that the continuous occurrences of the same letter is collapsed into 1. And then what we can do is basically train an ASR system which is able to generate these letters at different audio frames and then use that system to decode the audio. Now there is a problem with this particular setup, and the problem is following. So how do I represent the letter sequence B, E and E in my output? Because if I collapse the continuous occurrences of E, then I can never output 2 continuous occurrences of letter E, right? So my true word in the transcript is now B, E and E corresponding to 7 audio frames, and the heuristic that I had made, I cannot actually represent that sequence of letters. Let's now look at how we can represent continuous occurrences of same letter in our output transcript. In order to do this, there is an extra symbol introduced called blank symbol, and this is the idea introduced in Knecht's temporal classification or CTC based ASR systems. And here is how it could work. So for example, what we say is that I am emitting a blank at frame 1, I am emitting B at frame 2, I am emitting E at frame 3, I am emitting blank at frame 4, I am emitting E at frame 5, E at frame 6 and E at frame 7. Now if I collapse the continuous occurrences of letter E from frame 5 to frame 7, it becomes a single occurrence. At frame 4 I have a blank, at frame 3 I have a E, and at frame 2 I have a B, and at frame 1 I have a blank. You can think of blank as also like emit nothing. So since at frame 1 I emitted a blank, this is basically saying emit nothing. At frame 2 I emitted B, so I have the first letter of my word in my transcript B generated. At frame 3 I emitted the letter E, so I have the second letter in my transcript. And at frame 4 I emitted a blank, so I say I did not emit anything, but the blank at the frame 4 is kind of separating what I have emitted at frame 3 and what I have emitted from frame 5 to frame 7. So continuous occurrences of letter E from frame 5 to frame 7 will be collapsed into one occurrence. So from frame 5 to frame 7 I have single E, at frame 4 I have emit nothing, at frame 3 I have E, at frame 2 I have B, and at frame 1 I have emit nothing. So now I can represent the letter sequence B, E and E with this introduction of blank. And with that we kind of finish the discussion on CTC based ASR systems. One of the thing to note here is that we are making a huge conditional independence assumption. So while generating the probability distribution at any audio frame, I am only using the audio history. I'm not using what transcript I have produced up to that point, right? And that's a huge conditional independence assumption. So for example, let's say I was generating the word Obama in my transcript, and if I have already generated OBA, then using the fact that I have generated OBA, my model should be able to assign a high probability to the next letter being M because of the history of what has been produced so far. In CTC, you are not using that fact, and we will remove this conditional independence in RNNT based ASR systems. So far, we have looked at two different ways of building non-modularized or end-to-end ASR system. First, we looked at LAS and then we looked at CTC. As we have seen, in CTC, we make conditional independent assumption on text history produced so far in the transcript while generating probability distribution over output symbols at any given audio index. CTC, though, would let us build a streaming ASR system. For an example, let's say an audio has 10 audio frames in it and we are decoding it in a streaming manner. At audio frame index 5, the probability distribution over output symbols would only depend on audio history up to index 5 and will not depend on what has been produced in text history by utilizing audio frames from index 1 to 4. In LAS, we are conditionally dependent on both the full audio and text history produced so far in the transcript, and hence it has much lower conditional independence assumption than CTC. But in its natural setting of LAS, we cannot build a streaming ASR system. Here is how RNNT comes in the picture. In RNNT, along with audio encoder, we also have text predictor, which lets us utilize the text history produced so far while producing probability distribution over output symbols at any audio frame index. And hence, it removes the conditional independence assumption. However, unlike LAS, in RNNT, we do not need to have full access to the audio and can decode as the audio is becoming available. Since RNNT does not have to depend on the full audio, so it would let us build a streaming ASR system. We would look at more details of different components of RNNT ASR and how to train and decode with RNNT ASR systems shortly. Before I get into details of RNNT based ASR system, let's look at why RNNT based ASR system would be a favorable approach for a production kind of system. So RNNT would be able to help us build a single component based non-modularized ASR system. Since it is a single component, it would be compact and hence it could be deployed on device applications. RNNT, as I explained, would also let us build a streaming ASR system without making the conditional independence assumption on the transcript, and it gives us very competitive metrics corresponding to the performance for ASR systems compared to modularized ASR systems.